Hello my people, I'm back again with the third video. My name is Kelvin Gibson and today I'm taking you through multiple linear regression with Python programming without regression packages such as sklearn, scipy, tensorflow and keras. In the last two videos it was simple linear regression. And the first video was simple linear regression with Python, and the second one was also simple linear regression with Microsoft Excel. So simple linear regression, in simple linear regression we use only a single predictor variables, but in multiple linear regression we are using more than one explanatory or predictor variables. We are trying to predict the cells based on the other number of regressors. Remember, we try to predict the cells based on the regressor number of TV shows. Nevertheless, there is a possibility that there is more than one regressor that influence the cell's response variable. We have now found that the other regressors could be the radio advertisement and the newspaper advertisement. So in this case, we will create this model with Python programming without the use of Python packages such as sklearn, scipy, tensorflow, and keras. Working on machine learning without the use of Python packages is very important in understanding and interpreting what is happening when using the Python packages or any other statistical software such as R, SPSS, STATA, and Microsoft Excel, with addins such as regressit and Analysis Toolpak. However, the method demands deeper understanding of statistics and Python programming. In addition, it's tiresome and time-consuming, but this is a requisite for any statistician, data analyst, data scientist, and mathematician. In statistics, we will require the application of mathematical knowledge such as linear algebra to work with matrices and vectors. If you are comfortable enough, you can just download the Python file with the link below here, and you can just go ahead of me and start working on it. And if you are not confident enough, then don't worry, we will go a step by step together to work on it to build this model. So what we will do in this video, we will build our model and predict. That's first step. The next step will be analysis of variance table and over. The third one, model variance. We calculate the variance of the model. The fourth step, standard errors of the coefficient. The fifth one, t-statistics. We'll compute all of those t-statistics. Sixth one, confidence intervals for coefficients. Seventh is model evaluations, and include R squared, adjusted R squared, and some mean square error, root mean square error, and mean absolute error. And the last step will be model representation and assumption testing such as homoscedasticity, normality, independence of variance or errors, and all. Okay, now before we start, I'll just run this code so that I'll just hit shift enter and you can see this is my name. I'm Kelvin Gibson, the statistician and analyst. Next, I've also provided the formulas for each and every step which we will going through. Okay, now let's start. We will require to fill these gaps so that as we move forward, so that our model will be completely successful. Okay, now let's import pandas SPD. Next, import numpy snp. Third one, import matplotlib.pyplot.splt. And that one, import scipy.stat, import f. And if I hit shift enter and run this code successful, and let's import our data. Our data is called advertising advertising.csv. And don't worry about the data, I'll also provide the link so that you can access and download this data. So if I hit shift enter, then we have our data. Next, and you can see our data are having 1, 2, 3, 4, 5 are having 5 columns, and I also forget to add here print df dot shape, so that's see how many the dimension of our data. Sorry, just use the wrong name of data frame. And we're having 5 columns and 200 rows. You can see this is very difficult to work on hands or use of Excel. It's very tiresome. So here in this our data, TV, radio, and newspaper will be our explanatory variable, which will try to explain or to predict the cells, which is our dependent variable or predictor variable. In the previous video, we were using TV as the only explanatory variable, but in this case now we will use the 3 columns or 3 explanatory variables to predict the cells. This first column, which is called unnamed, we will not be using it as it's not serving any purpose, so we'll have to exclude it, and we will only remain with 4 important columns. Okay, let's continue. So inputs will be our explanatory variables, so we'll have to list all our explanatory variable. And here if you see, it's the first one is TV, radio, and newspaper. That's okay. Then we'll have to add another important column, which is for constant. Yeah, it's very important. That's why we are using matrices. It's very important in matrix. That's why we'll add another extra column called we'll call it constant. It includes a column of ones, and this is how we build this column. We'll use np.ones, and we'll have 200, just like the number of the original data. It should contain 200 rows of ones values, and then we will convert it to data frame, and we will name the columns as constant. And next, this is our explanatory variable. Now next we'll have to join these two data frame. We have the first data frame is our explanatory variables, and the next one is a data frame with values of ones. So we'll have to merge or to join these two data frames and become ones, and we'll call it X. So how will we make this one? We just use pd.concat function. It will just concatenate the two data frames, and if I hit shift enter, then now we have been 5 columns, and if I want to see, we should at least see the first 5 rows, defer X, and you can see here below we are having a new column called constants, and there were our original columns TV, radio, and newspaper. And now we are ready to go. Another thing is our predictor variables, which is y. I've just indexed the values for cells. This has no more steps. Next, now remember from our formula above here, if we want to obtain the coefficients, we must use this formula. We must use this formula, and we are starting with this first part. We multiply the transpose of explanatory variable times the explanatory variables, then we find the inverse of this matrix. Then after we have just calculated the first part, we go on with the second part, whereby we also multiply the transpose of explanatory variables with the y response of which now it's cells. So let's work on it. So I'll go down here. and convert this data frame to a matrix. So I'll only use x is equals to np.matrix x. Then I will just want to see first 5 rows. If I hit shift enter, then you can see it's a matrix. Even here it's written matrix, and we are okay now. Now we have converted our data frame to matrix. Now we want to find this transpose of explanatory variable, and this how we transform it. We use np.matrix.transpose, then we put here inside the bracket x. We name this matrix transpose as xt, and if I hit shift enter, now we have transposed it successfully. Next, we want to find the y values of the cells, but in the previous steps we already calculated it. Now what we want to do now here is to transform from data frame to a matrix form, and there we are using np.matrix and find it transpose. So now here, if I hit shift enter, then you can see we have transformed it successfully. Next, we have found the transpose of explanatory variable. So next, what we want to do is to multiply the transpose of explanatory variables and the value of explanatory variable. How do we multiply the matrix in Python? We just use np mirror that way, and if I hit shift run, we'll multiply the two matrices successfully, and here we have the multiples of our matrices. So the remaining step is to convert this matrix into the inverse, but we will do it later. Now let's go now to the second part of the formula. The second part of the formula was to multiply the transpose of explanatory variable and the response variable. So let's go to the second part now, but remember we have not converted this first part into the inverse. We will multiply both of them together while we are converting the first part to the inverse. Now let's multiply the second part first. So down below here, in fact has been already done. What I only need to do is just to hit shift enter and run successfully. Okay, now we have done with the second part. Now we need to multiply the first part and the second part here. There is a problem here with this formula. I have to correct it. Let me do it. I'll just I need better. Yeah, if I hit shift enter, yeah, it should be that way. Okay, now we want to obtain our betas, and remember we need to transform this first part into the inverse. How do we convert it into inverse? We will simply use Python formula for numpy called inv, inverse for inverse. And if I hit shift enter, shift enter, now I have obtained. What I forgot to do is to add base.inv. Sorry guys, but don't worry, things is working well now. We are in the right track. Okay, next. Now we have found the betas, we have found the estimates. From the estimate, this one is beta note, and if to access this beta note, we just work on the way we usually work on the numpy. I'll just set by hit 0 here, and if I hit shift enter, we obtain our coefficient of intercept, and it's 2.939. Next, I want to access the coefficient. There is more than one coefficient, and I'll just use this sign, and it starts from 0 onward till the end. Those are the coefficient, and here we have 2.39, 4.5, but it should not be more than 4, more than 3, sorry, it should be more than, it should start from 1 and onward. Yeah, and here I have, this is my coefficient for TV, this next one is coefficient for radio, and the last one is coefficient for the newspaper. There is information below which explain it well. It has actually summarized what we are expecting. So estimate for intercept or coefficient intercept is 2 point TV, radio, and newspaper. Sorry, I forget. What did I forget to do? No, we are on the right track. I'm sorry. I don't know why I'm doubting myself, so should be so. Okay, now let's continue. What else do we need? Now we have just successfully created our model. So the next step is to predict our model. Now in prediction, when we are predicting our model, there is a special formula for NumPy which is usually used for working with the matrices, and it's called x dot dot x dot. These explanatory variables are multiplying them with our estimates, and if I hit shift enter, then we will see our predicted values. Let me do it. Hit shift enter, and here we have our predicted values for our model. You can say it's not very difficult as long as you are understanding these formulas. The formulas is what is guiding us through all these processes. These formulas are very important. Now we have done with the step 1. Now we have done with the model prediction and model building and predictions, and now we are in analysis of variance. So before we start this model and variance, we have to find or to compute the variance of the model. So now we are in step 2, analysis of variance of the model. So here is a formula. This actually is the residuals, and the formula is the formula is this one. This we are squaring residuals. This is sum of square of error, sum of square of model R or regression, sum of square of total. This is the formula, and there is an alternative formula for sum of square of total. So here n is the number of observation, and now we are having 200 rows. N is equals to 200 observations. P is equals to k plus 1, of which it means the number of regress as is k, plus 1 is intercept coefficient, and k is our effect self-explanatory. So variance, just as I've said, we need to first compute the value for variance. How do we go about? So here, first of all, we will use a formula. This step or this formula tell us to find the transpose of y. So I'll just repeat it again. I remember we did the previous step, but there is no harm of repeating. I'll just use the formula transpose from NumPy, dependent variable, and then after finding it transpose, we are multiplying it with the value of transpose. That's why we are using matmult here. And if I hit shift enter, we get a single value, and this is our result. Okay, let's go on. We are in the right track. Whoa. Okay, now next, let's follow the formula. Remember, we are following this formula. We're trying to calculate the sum of square of error, and we can't calculate. We are calculating sum of square of error so that we can get the variance estimate of the model. That's why we are starting by calculating sum of square of error. And sum of square of error, sorry guys, I didn't explain it to you. Sum of square of error, this is the formula. But this formula for simple linear regression. If for the case of multiple linear regression, we are using this formula. That's why we have just transform this to transpose, then multiply with this one. Now we are in this second part here, whereby we'll multiply the estimates for the model times transpose of explanatory variables, and finally multiply with the predicted, not predicted values, by the actual values. Also, we can also use this formula for simple linear regression, but now let's first use this second one. Now we are in this second part. We have done with the first part, now we are in the second part, where we are multiplying the estimates times transpose of explanatory variables, and finally multiply the answer with the predictor variable or a dependent variable. Now let's go on. Where were we? So here, we are now here. We have just calculated this one. Now we are here now. Now A will be multiple of our estimate of coefficients and transpose of x. This is the first step. The second step will be we will multiply the result which we have found above times the predictor variables. Then here we'll find the SSE which we are looking for it, so that we can use it to find the variance of the model. So SSE, to find the SSE, if I hit shift enter, I'm getting 556. Yeah, now I have 556 as my SSE, and the variance, I've just computed all these ones. Remember, SSE over ln over the length of all the data dimensions minus the length of p. This is the formula we are working with. SSE over n over p. But remember, SSE, we have to divide it with the total dimension minus the estimates of the model plus 1. P is equals to k by 1, where k plus 1, where k is the number of regressors and 1 is the coefficient that were here. Of those are not. How many of these? So now here we are in the right track. Now which step are we now? Now we are in this step, whereby now we have variance of 2.841. This variance we will be using it at a later stage. Now let's go on with another table. We have just calculated the first part. So here now, alternatively, now let's use the second part and confirm if the answers are the same. I remember I said that we can also use the second. We have two methods for calculating SSE, and this one is the second method. So let's run this code, because it's an alternative way. If I hit shift enter, we're having the same answer, 2.841, 2.840. Round off, they will become the same. They will all look same. No. So now I can also run this code. I want to see my estimate, and the value is 556. So now let's go on with sum of square due to regression. Just computed sum of square due to error or residue. This about unexplained number. This is the variance which cannot be explained in the model. Now let's go on to the variance which can be explained by the model. So here, the first step, remember we computed these ones. We have these ones already. And what we need now is to compute these second parts. We need to sum all of the predictor variables or dependent variables, and we will have to square it first, then sum and divide by the number of the observation of which is 200. So, and if then we come here, sum of square due to regression will be simply we got the value of b as the value of these first parts, and now we are subtracting the second part. And if I hit shift enter, I'm getting 4860, and it's obvious it's more than SSE. We are in the right track. Let's move on to the next step. The next step, we have this code. We are now at the stage of calculating sum of square due to the total. So this one has two formulas, and the first one, let me show you where is the first formula. Yeah, in fact that's being shown here. So the first formula is to subtract the sum of square of the response variable, and of course it's called y-mean. We've computed before. It's called y-mean, and then if I hit shift enter, we're getting 5000. And obviously this usually or normally the largest of all, since it's the sum of square of total. And the other formula is just, we can just add what we've gotten, SSE, value of SSE here, and value of SSR, sorry, and we just arrived at the final answer. And I can confirm by hitting shift enter, and I expect the same answer. And can scroll down, scroll up, then we can compare, and actually they are the same answer. Now we are on the right track. We are now ready to build our ANOVA table. So our ANOVA table, these are the formulas for ANOVA table. Remember that ANOVA table have some degree of freedom for each and every sum of squares. For example, here sum of square of regression or model is n minus p, and we knew how p is being calculated. P is just equals to regressors plus coefficient, number of regressors plus number of coefficients, and n is equals to number of our rows. Then if we take the number of, if we take p from 200, it will become 296. Okay, now let's go on. Mean square error. The degree of freedom of mean square error is just the number of rows, all observations, minus k, of which k is total number of regressors only. And then mean square due to total, we are just taking one from the number of rows, and it will become 299. The next step is F statistics. F statistics equals to mean square error due to regression or mean square error due to residue or error. And if you want to compute p-value, p-value, you can remember p-value is very difficult and to compute, and there is a special formula in Python. That's why I imported this f here. This one will help us in computing the p-value for ANOVA table or f-test table. Let's go back and work on it. Where is it? Where were we? Yeah, we are here. We were here. So now p-value take three important arguments. The first one is f statistics, which will come from this formula. The next one is the degree of freedom for sum of square due to regression. And the last one, degree of freedom due to sum of square of residue or error. And k is the number of regressors, and is the number of summation, n is equals to 100, p is equals to k plus 1. So p is equals to number of regressors plus intercept, p equals to 3 plus 1, and it's total to 4. So now here I've just constructed my data frame, which will simplify all the ANOVA table. And the formula for creating ANOVA table is equals to pd dot data frame. And if I hit shift enter, now here we have our ANOVA table. So sum of square due to regression is of the values. We computed these values. These are the degree of freedom. Here is mean square error. Is f statistics, and this is the p values. Now we have completed step 2. We have just computed the ANOVA table. So the next step is the model. Model variance. We calculate the model variance before ANOVA table. We have done with these first 3 steps. The last step is standard error of the coefficients, and we will combine the 4th, 5th, and 6th steps. Since once we have calculated some values here above, such as variance in ANOVA table, it's very easy to compute these values once. So now let's compute the 4th, 5th, and 6th steps. We will just do for a simple coefficient. Remember, these steps require us to do for each and every coefficient. That's why we will do only for the first coefficient, then we will copy and paste for the others. So do some editings, and finally we will bring all of them together and summarize them together. Okay, and then we move to the model evaluation. Okay, now let's start with t-statistics or standard error of the coefficients, intercept, t-statistics intercept, confidence interval intercept. Then we will copy and paste and do for the others. Then we bring together and we'll move to the next step. So here, down here, where were we? We've just completed this step. Yeah, it's just below here. Just below here. So now here, yeah, step 3, 4, and 5 will do it at the same time. So now t-statistics, this is the formula for t-statistics, and this is the estimate for any model coefficient. We will divide by square root of standard error for the same coefficient estimate and multiply with the CII. CII is the diagonal elements of the multiple of transpose of explanatory variable and explanatory variable itself. I have just explained here. CI are diagonal element of this matrix. And then p-value. We did p-value for F statistics. We have another task of doing a p-values for T statistics, and we'll use p-value is equals to t.esf, and this one take the previous one took 3 arguments, but this one will take only 2 arguments. The first argument will be T statistics, and we will put it in absolute form. It will not have any direction, whether negative or positive. And the second argument is the degree of freedom of sum of square due to regression, and since it two-tailed test, then we'll have to multiply by 2. Then confidence intervals. Confidence intervals, we are trying to see the range of our coefficients with where are these values ranging. For example, and by default the confidence interval is 95.5%, and since in Python I find it very difficult to compute this value, I just used Excel formula called t.inf.2t, whereby I take this statistics for estimates, which we have computed here. This t here I put here, then degree of freedom of sum of square of error, and then I found this value 1.9721. So this is the significance level values for these ones, and we will use it as our default. So now I think you are comfortable and you are getting it well. Now let's continue. In case of any question, you just comment and I'm ready to help to give any assistance. Okay, let's continue now. Just as I've said earlier, I only do for one coefficient, then we'll just copy and paste for the other. We'll just edit some values on how to access our matrices. So here I will start. So intercept is the diagonal intercept. Before that, I'll just copy this value here and just another cell here above. In fact, this one. Oh yeah, I just edit. I just remove this and have this one only. So I'll just convert this to code. But later, want to convert it to code. Yeah, this way. We will be accessing our values here, which we'll be using to find the standard error of intercept, T statistics for intercept, p values for intercepts, and upper and lower confidence intervals of the coefficient. So now this one, we are just finding the inverse of our multiple of transpose of explanatory variables and explanatory variables. Remember, in the previous step we didn't calculate direct. That's why we are calculating. That's why here we are calculating it direct here. so that we can use the below steps. If I hit shift enter, and these are the values which we are accessing to help us find more information on what we are looking for. So here I want to access these 3.4441 here. Now I'll just remember Python starts from 0. Yeah, so this will be 0 0. Python start from 0 0 0. Just put here row 0, then column 0 this way. I want this one. So next one, betas. I just add another cell here down and just access betas. We computed it above, so I want to access the intercept value, coefficient of intercept, and I want this 0, so it will be this first row of the index of the matrix. Sorry, so I just put 0 this way, and this one I'll just put the same as the latter one. And where else? Here, this paras I only want coefficient. This one I want 0. First row, first row, first column. Here, first row only. Just no more columns here. Here, first row, first column. That's why. Where else can I add some values? There is no any other path. Then if I hit shift enter, then wow, I'm having standard error for radio. Should it be for radio? No, start with intercept first. Should not be for the radio. Still start for intercept. It should be intercept. I can edit. Where else should I edit here? Intercept. That way. Then I can hit shift enter to correct. And now here we are having standard error for intercept. These ones. T starts for intercept. These ones. P-value. Upper limit 3.4, lower limit these ones. So what we need to do is copy and paste, then edit. So I'll not do that one. Yeah, so we are accessing the second row, second column. That's why I'm using 1 1, and we are accessing this one here is for the second coefficient, of which is a TV. And then you correct all of them. And after you have done, if you hit shift enter, you have your answer. That's for TV. The next one, why is this? I wonder where it's written radio. Should be for TV. Sorry guys. Yeah, TV. Yeah, and to correct them, I need to hit shift enter again, and there I'm having all information, including standard error, T statistics, P values, TV, tubular. Next is radio coefficients. Now we are in a radio now. We also we are in the third row at column, which is 2 2, since Python starts from 0, and the third coefficient or estimate. And if I hit shift enter after we have checked everything is okay, I'm getting the answer. This one's, we are in a right track. Last one, we are in the last row and last column for these values, and the last row for values here. That's why I'm using here 3 and here 3 3 5. Last row, last column of the matrix. And if I hit shift enter, that's what I'm getting. And we need to summarize all of them by bringing all of them in a single data frame. That's why here I create a data frame called summary, and I started with the coefficients. The coefficients start from this one for intercept 0, second one 1 is for intercept, third one, no, this one is for TV, third one is for radio, the last one is for TV. Then standard error, the same, I access all the above values. SE of intercept, I've just calculated in the previous step, we'll just bring all of them together here. And if I hit shift enter, then if I want to see what I've just prepared, just hit shift enter, and now you're having a lot of information. This intercept, this is where regression analysis come into hand. Now we can know which variables are important in predicting the cells here. So here I can come here to p-value, but I've not formatted it nicely. Let's use a t-statistics. We need the t-statistics with smaller values, and it's a newspaper. And if you see the, oh, where's my t-statistics? Yeah, and you can see that the p-value for newspaper is greater than 0.5, and this is insignificant regressors. So the most important regressors is the TV and also the radio. So standard error, you can see that TV has lower standard error, followed by radio, and newspaper has a larger standard error. So TV and radio are the important regressors for predicting the cells. Now we are in the last step. Let's go back and see where we are. Now we are in the step 6. Oh, we have done the step 6. Now we are in step 7, model evaluation. And here we need to evaluate how our model has performed. Now in model evaluation, we'll start first by calculating the adjusted R squared and R squared. So the formula for R squared is equal to sum of square due to regression over sum of square due to total. Alternatively, you can subtract sum of square due to regression residue or error over sum of square due to sum of square of total. So let's first use the first method, and since we computed the previous steps, you can just write the way the formula direct us. So formula equals SSR over SST, and if I hit shift enter, I'm getting a value of 0.897, which is almost 90%. So Our predictor variable can be explained by explanatory variables by 89.7%, which is it's good actually. Okay, now let's calculate adjusted R squared. Why are we calculating adjusted R squared here? Adjusted R squared for any regressors for any additional regressors which has no significance. The adjusted R squared penalizes, but R squared, as increases the regressors, the value also increases without caring whether it's significant or insignificant. But when it comes to adjusted R squared, it cares about whether you have had insignificant or significant regressors, and the value of adjusted R squared is normally lower compared to the R squared. Let's now shift enter. But before that, we need to subtract here the R squared. The formulas explain that we should subtract here value of R squared underscore SQ. That way, but I should here put here capital S since Python is case sensitive. And if I hit shift enter, I'm getting 0.896, and before we got for R squared 0.897. You can see the difference is 0.001, and that's okay. Now let's go on. Now the next step is that I should run this one, reverse formulas. Now here we need to find the mean square error, root mean square error, and mean absolute error. On this step, the formulas are shown above. Mean square error is equals to 1 is the difference between the observations and estimated. Then you square the value, add them, and divide by the number of observations. Mean absolute error, instead of squaring the difference of the observations and predicted values, you simply find the absolute values, then divide by it, sum them, and finally divide them by the number of observations. Root mean square error, you simply take the square root of mean square error. Now let's see the values by putting MSE, just copy pasting here. Then RMSE, and if I hit shift enter, you can see we have just completed all of everything here. Mean square error 2.7, mean absolute error 1.25, root mean square error 1.66. Okay. We already did these ones. We have already done with these ones. Here you can simply, maybe you can summarize SSSE. Here you can simply copy paste here R underscore ISQ underscore, and here I want to copy paste these ones. Copy paste here. If I hit shift enter, getting all of the values summary here below. So next we need to visualize. First one, we'll just use plots, and the second one also plot. Want to plot to compare the predicted, and if want to compare the actuals and the predicted, and if I shift enter, we can see that the model is actually doing well. The next one, independence of error of residuals, and this one we simply everything is complete here. You only need to use shift enter, and yeah, you can see that the residuals, the errors are randomly scattered along this vertical line, and there is independence of variance. And the next one, this one, homoscedasticity. If we shift enter, we need here to use plots, scatter, and if I hit shift enter, you can see the values are randomly scattered. There is no special shaped formed concept, and we can conclude that it is it's homoscedasticity. There is a constant variance. And the last step, we can plot histogram to compare the distributions of the predicted values and residue. plt.hist also, and if I shift enter, we're getting the nice histograms. You can see the residuals and normal distribution values are almost similar. The only difference is the sizes, but the distributions are similar. So conclude that there is normality for residuals. Okay guys, thank you again for watching this video. We have actually come to an end of this video, and I'm very grateful for you guys taking my time to watch this video. My name is Kelvin Kipsang, and let's meet in the next video. Please don't forget to like, share, comment, and subscribe. Let's meet in the next video. My name is Kelvin Kipsang, the statistician and analyst. Thank you.